Hello everybody. We are going to solve a problem now on the minor losses calculations for one of the cases that we discussed last time. So this problem is kind of tailored for just the minor losses calculation. It doesn't include any major losses. But what we do here is just part of the solution. If we have both major and minor losses, we'll just add both types of losses together to get the total losses. So here we have a pipe that has diameter of 6 centimeter that is gradually expanded to 9 centimeter diameter, and we know the velocity is 7 meter per second, the pressure is 150 kilopascals, and we know that the expansion section or the walls of the expansion section are angled 10 degrees from the axis, so this angle is 10 degrees. So both angles are going to be 20 degrees. We need to find the head losses in the expansion section and the pressure in the large diameter, and we know the kinetic energy correction factor. So if you want to calculate the pressure at the outlet, we have to apply Bernoulli equation, and the losses will be part of the solution. So we will do this or the solution this way. So the first thing we can do is to calculate the velocities. So we know the area in the small section or the small diameter section and the area in the large diameter section, and we know the velocity here. So by applying the continuity equation, we can find the velocity at the product stream, which is u1 times a1 over a2. And now, by applying Bernoulli equation, we know that the height of the 2 points is the same. That this is we know the pressure here, we know the velocity and the velocity. So the Z1 and Z2 are equal. There is no pump, there is no turbine. So the rest of the terms or these terms will be cancelled, and we will only have the P1, the U1 square and U2 square, and the losses. So we know these terms, but we only miss the losses. So to calculate the losses, it's only minor losses here. And as I just said in the beginning of this video, that it's just tailored to be focusing just on the minor losses. So the losses is equal to KL times U1 square over 2G. And the K can be got from the tables, and I already cropped the part of the table of interest to us here, which is the gradual expansion, and it's only given for the angle of 20 degrees, which is 10 degrees here and 10 degrees here. So it's the only case that we have in our textbook. You will see there are different values of KL for the different values of D over D. So we have 0.2, 0.4, 0.6, 0.8. So for our case, we have 6 over 9, which is 0.667. So it's going to be between these two numbers. So the corresponding KL would be something between these two values. It's expected that it's going to be closer to the 0.15, so it can be 0.14 or 0.13. And you can get the number kind of like an estimation, but if we want to get kind of accurate value, we can do linear interpolation, which means that we can assume that we'll pull the data from the table, and we can assume that the ratio or the relation between D over D and KL is a linear relation, which means that the slope is constant. So we can say that the slope between these 2 points, which is delta y over delta x, 0.15 minus 0.1 over 0.6 minus 0.8, this is the slope, is equal to the slope between these 2 points, which is the unknown k minus 0.1 over 0.667 over 0.8. So this is what we can do, and from this we can calculate KL, and it came kind of what we expected. I'm sorry. So it's between or closer to 0.15, between 0.13 and 0.14. So the next step are going to be very systematic. We'll just multiply KL times U square over 2G. And if you remember, we said that this table or the case that we get from this table are based on the velocity in the smaller diameter part. So it's going to be multiplied by U1. This is why I put it as U1 square over 2G. And now we can get the losses, and we can substitute in Bernoulli equation. And from this we can get P2. And this is what we need to calculate. But there is just one quick note here, that if you check the value of KL or the pressure at the exit stream, you would notice that it's more than the pressure in the feed stream. So it's here 150 and it comes out at 167. And this is not a mistake, and this is expected because the although we have losses, but we have energy transformation from here to here. The pressure is transformed into, I mean, the kinetic energy is transferred into pressure. So pressure increased because of the decrease in the kinetic energy, and there is some losses as well, or there are some losses as well, but the increase due to the conversion of the kinetic energy into pressure is more than the decrease due to the losses. And this is something we mentioned at the beginning of our discussion on the losses, that we said that the losses are irreversible, while the energy transformations are reversible, which means that if this pipe goes back to a contraction pipe, which means that it goes back to the original diameter, the velocity will increase and the pressure will decrease. So it's kind of a type of energy that we can recover or convert from a form to another, which is not the same case for the losses, which are irreversible losses. So this is the example that we will solve, or we have for this video. I'll try to solve a couple of, or one or two more examples that will combine both the minor and major losses later. But for the next video, we're going to discuss the pumps. There is like a very important thing we need to discuss about pumps, that we keep this for the next video, inshallah. So I'll see you then.